You have likely seen the stunning imagery beamed back by the James Webb Space Telescope. Those dreamlike portraits of deep space galaxies, radiant nebulae, and cosmic structures so intricate they almost defy belief. But while Webb observes the universe from orbit, a machine just as formidable has quietly awakened right here on Earth. High atop a remote peak in Chile, a brand new observatory has opened its eyes for the very first time. Yet, what it has just captured isn't merely a beautiful snapshot. It is something far more unnerving and far more critical. These are the debut images from the Vera C, Rubin Observatory, taken with the largest digital camera humanity has ever constructed. These images are so vast, they cannot be viewed in a single glance. They don't just display the universe. They record its evolution. This isn't about seeing deeper into space. It is about seeing everything all the time. Once you grasp the true purpose of the Rubin Observatory, you realize these initial photos aren't the mission's highlight. They are the warning shot. At the core of the Rubin Observatory lies a camera unlike any other in existence. Roughly the size of a compact car and weighing nearly 3 tons, this singular instrument captures images boasting an astounding 3.2 billion pixels per exposure. To display a single one of these images at full resolution, you would need approximately 385 4K televisions. That is not a metaphor. That is the raw scale of data generated every time the shutter clicks. In just one night, the observatory can amass up to 20 terabytes of data. So much information that a dedicated 100 gigabit fiber connection had to be laid just to stream it from Chile to data centers in the United States. However, the objective was never just resolution. It was coverage. Every image spans a section of the sky equivalent to 45 full moons. This means the Vera Rubin Observatory can photograph massive swathes of the universe in a single shot while still resolving faint stars, distant galaxies, and the subtle cosmic structures hiding in the background. This is not a telescope built to admire the cosmos. It is a telescope built to inventory it. Space telescopes like Hubble and Webb bypass Earth's atmosphere entirely to get clean, undistorted views. So why construct something like Rubin on the ground? The answer is location. The observatory sits atop 𝗺𝗶𝘂𝘁𝗁 in Chile's Atacama Desert, one of the driest, darkest, and most stable viewing environments on the planet. With minimal atmospheric turbulence, virtually no cloud cover, and exceptionally low light pollution, this region offers conditions that rival space itself. Rubin also utilizes a revolutionary 3-mirror design. Unlike the standard 2-mirror setup found in most telescopes, its optical system employs 3 precisely shaped mirrors to correct distortions and maintain sharp focus across its massive field of view. This allows Vera Rubin to see wide and sharp simultaneously, capabilities previously thought to be mutually exclusive. The result is a ground-based observatory that competes with space telescopes in clarity while surpassing them in speed and scale. When the first official images dropped in June 2025, astronomers hailed them as some of the most breathtaking views ever captured from Earth. One image, dubbed the Cosmic Treasure Chest, is a colossal mosaic of the southern Virgo cluster, sitting about 55 million light-years away. Constructed from over 1,000 individual exposures taken over 7 nights, it unveils a region holding roughly 10 million galaxies. Yet, that image represents a mere 0.05% of the galaxies Rubin is expected to catalog during its full survey. Zooming into the mosaic reveals spiral galaxies interacting, merging systems stretching tidal streams between them, foreground stars from our own Milky Way, and a backdrop of faint reddish galaxies reaching deep into cosmic time. Another early image displays the Lagoon Nebula in astonishing breadth and color, exposing star-forming clouds and clusters that would typically require years of observation to assemble. Rubin captured it in hours. These aren't curated highlights. They are routine outputs. What truly distinguishes the Rubin Observatory from every telescope before it is not what it sees, but how frequently it sees it. Over the next decade, Rubin will repeatedly scan the entire southern sky every few nights, creating a time-lapse movie of the universe, a record of change. It will track exploding stars, shifting asteroids, pulsing variable stars, and even interstellar objects passing briefly through our solar system. In just 10 hours of test observations, Rubin already identified over 2,000 previously unknown asteroids, including several near-Earth objects. Over its lifetime, it is expected to uncover millions more, alongside countless transient phenomena that appear and vanish before most telescopes ever notice them. By the end of its survey, Rubin will have gathered more optical data than all previous observatories combined, generating around 500 petabytes of information. This isn't astronomy as observation. This is astronomy as surveillance. The universe will no longer be something we visit occasionally. It will be something we monitor continuously. For most of human history, the night sky felt permanent. Stars rose and set. Constellations remained fixed, and change, if it happened at all, was too slow to perceive. Rubin destroys that illusion. By scanning the sky every few nights, the observatory transforms the universe into a living system, one that flickers, shifts, and evolves in real time. Supernovae appear where nothing existed before. Variable stars pulse like cosmic heartbeats. Asteroids drift silently across the background, revealing their motion only when viewed again days later. This is why the 10-year duration of the survey is crucial. Rubin isn't just collecting images. It is building a temporal record of the universe, frame by frame, change by change. For the first time, astronomers won't just ask what the universe looks like. They will ask how it behaves. Some of the most violent events in the cosmos are also the most short-lived. Supernovae flare and fade. Gamma-ray bursts vanish in moments. Interstellar objects pass through the solar system once, never to return. Until now, many of these events were discovered too late, after they had already peaked or disappeared. Vera Rubin flips that equation. Because it revisits the same regions so frequently, it can detect sudden changes almost as they happen. A star that wasn't there last week suddenly appears. A galaxy brightens unexpectedly. An object moves against the background stars in a way that betrays its proximity. This rapid detection allows other observatories to respond in real time, slewing space telescopes and ground-based instruments toward targets Rubin flags automatically. Rubin isn't working alone. It is becoming the universe's early warning system. While Rubin is famous for deep space, one of its most immediate impacts will be much closer to home. In just 10 hours of preliminary observations, the observatory identified more than 2,000 unknown asteroids, including several near-Earth objects. And that was before the real survey even began. Over the first 2 years alone, Rubin is projected to discover millions of new asteroids, vastly expanding our catalog of solar system objects. It may also become our best tool for detecting interstellar visitors like 𝗺𝗶𝘂𝘁𝗄 and 𝗺𝗶𝘂𝘁𝗲, objects that originate beyond our sun and pass through only briefly. These discoveries aren't just scientific curiosities. They improve planetary defense, help us understand how solar systems form, and offer rare samples of material from other star systems. Rubin is turning the solar system into a monitored environment rather than a static diagram. By the end of its mission, the Vera Rubin Observatory is expected to generate around 500 petabytes of data. That is 500,000 terabytes, encompassing billions of objects and trillions of measurements. This dataset is so vast that no single research team could ever exhaust it. Instead, Rubin is building a legacy archive, a resource that astronomers will mine for decades, finding patterns and phenomena the original designers never anticipated. Discoveries will emerge not just from new observations, but from new ways of querying the same data. In many ways, Rubin represents a shift in how science itself operates, from isolated experiments to continuous observation, from snapshots to histories, from small datasets to cosmic-scale information. The telescope is no longer just an instrument. It is an engine of discovery that will keep running long after its first images fade from the headlines. What Rubin is truly doing is something no telescope has ever achieved at this scale. It is converting the sky into a movie. Every few nights, the same regions are photographed again and again, creating a continuous record of change. Stars brighten and fade. Galaxies subtly shift as supernovae ignite within them. Objects appear, move, and vanish. This time domain approach is revolutionary because the universe is not static. It is active, restless, and full of events that are easy to miss if you only look once. Vera Rubin doesn't just ask what exists, it asks what happens. This allows astronomers to study cosmic processes as they unfold, not long after the fact. The sky becomes a living system, one that can be replayed, rewound, and analyzed frame by frame. For the first time, the universe is not just observed, it is monitored. Rubin's repeated observations also allow scientists to detect extremely subtle effects that only emerge over time. One of these is weak gravitational lensing. As massive structures dominated by dark matter bend space, the shapes of distant galaxies are distorted ever so slightly. Individually, these distortions are almost impossible to detect, but across billions of galaxies, patterns begin to emerge. By measuring how galaxy shapes change across the sky and over time, Rubin will help map the invisible distribution of dark matter with unprecedented precision. This is not a direct image. It is a statistical revelation. The motion, alignment, and distortion of galaxies become clues, fingerprints left behind by something we cannot see but know must exist. Rubin adds time to this picture, making those fingerprints clearer with every pass. Dark matter does not glow, but it leaves tracks. Most observatories are limited by scheduling, weather, or the need to focus on specific targets. Rubin was designed differently. Its mission is repetitive by design. Night after night, year after year, it does the same thing with extraordinary consistency. Scan, record, repeat. This makes Rubin uniquely suited to discovering the unexpected. Rare events that might be dismissed as noise in a single image become obvious when seen repeatedly. Slow changes that would take decades to notice suddenly reveal themselves as trends. Patterns that require patience finally come into focus. Rubin does not chase discoveries. It lets discoveries come to it. And because its data is public, researchers around the world can search for their own signals, anomalies, and surprises, turning the telescope into a global scientific resource. As Rubin builds its massive archive, something subtle but profound happens. It establishes a new baseline for astronomy. Future observations won't ask, "What does this object look like?" They will ask, "How does this object compare to what Rubin already recorded?" Whether it's a newly discovered supernova, an unusual asteroid, or a mysterious transient event, Rubin's dataset becomes the reference frame against which everything else is measured. This fundamentally changes how discoveries are validated. Instead of relying on isolated observations, scientists can check an object's entire recorded history, when it appeared, how it evolved, and whether it behaved normally or strangely. Rubin is not just expanding our knowledge. It is redefining how knowledge is confirmed. Astronomy has always struggled with a trade-off. You could look deep, or you could look wide, but never both at once. Telescopes either zoomed into tiny regions of space with exquisite detail or skimmed across large areas with limited sensitivity. Vera Rubin breaks that rule. It combines an enormous field of view with the ability to see faint objects, and it does so repeatedly. This means that scale and speed are no longer opposing forces. They reinforce each other. In practical terms, Rubin can detect faint galaxies billions of light-years away while simultaneously tracking fast-moving objects in our own solar system, all within the same observing strategy. The same system that maps the distant universe is also watching nearby space for change. This convergence is unprecedented. The universe is no longer divided into deep space and local space. It becomes a single continuous system observed under one framework. Rubin doesn't specialize in one domain, it unifies them. One of the most radical aspects of Rubin is how it changes the discovery process itself. Traditional astronomy starts with a question. You apply for telescope time, You point the instrument, and you look for a specific answer. Rubin flips that model entirely. Because it scans everything all the time, discoveries do not need to be predefined. They emerge. An object brightens unexpectedly. A star dims in a way that defies known behavior. A transient flashes and vanishes before anyone knows what it was. Rubin captures it anyway. This opens the door to phenomena we don't yet have names for, events that don't fit existing categories, signals that would have been missed simply because nobody thought to look for them. Rubin is not limited by imagination. It observes first, and theory follows. While deep space often steals the spotlight, Rubin is also transforming how we understand our own galaxy. By detecting variable stars like RR Lyrae across vast distances, Rubin can map the outer halo of the Milky Way with unprecedented precision. These ancient stars act like cosmic beacons, marking structure, motion, and history. Over time, Rubin will reveal streams of stars left behind by smaller galaxies that were torn apart and absorbed by the Milky Way. Ghostly remnants of past collisions stretched across the sky. This turns our galaxy from a static picture into a living record of interaction and growth. The Milky Way is not finished. It is still assembling itself. Rubin allows us to see that process unfolding quietly in our own cosmic backyard. Perhaps the most important thing to understand about the Rubin Observatory is that its greatest discoveries may not happen tomorrow or next year, or even within the first half of its mission. They may happen years from now, when patterns emerge that no one initially noticed, when rare events accumulate enough examples to be understood, or when new analytical techniques unlock hidden structures in old data. Rubin was built not just for current science, but for future science, for questions that haven't been asked yet, for researchers who haven't been trained yet, for discoveries that require patience. This makes Rubin less like a traditional telescope and more like an archive of reality, constantly updating itself night after night without bias or preference. The universe is moving. Rubin is watching. The Vera C. Rubin Observatory did not arrive to give us prettier pictures. It arrived to change our relationship with the universe itself. For the first time in history, we aren't pointing a telescope at the sky and hoping to catch something extraordinary. We are watching everything, everywhere, all the time. The universe is no longer a distant object we observe occasionally. It is a system we monitor continuously. Stars pulse. Galaxies collide. Asteroids drift. Explosions flare and fade. Objects from other star systems pass silently through our own, and none of it happens in isolation anymore. Rubin sees it all, records it all, and remembers it all. This is not astronomy as exploration. This is astronomy as awareness. The true power of Rubin is not its mirror, its camera, or its data rate. It is the fact that it turns time itself into an observable dimension. It allows us to witness change on cosmic scales, to see patterns emerge where once there was only noise, to catch the universe in the act of becoming. And there is something quietly profound about that. Because when you watch the universe change night after night, year after year, you begin to realize that permanence was always an illusion. The sky was never fixed. We just weren't looking often enough. Rubin reminds us that we live in a dynamic cosmos. One that does not wait. One that does not repeat itself. One where every moment is unique, fleeting, and unrepeatable, just like us. This observatory carries the name of Vera Rubin for a reason. She revealed that most of the universe is made of something we cannot see. And now, the telescope that bears her name is revealing that most of the universe is also something we were never watching closely enough. That era is over. If you want to stay connected to a universe that no longer stands still, if you want to witness discoveries as they happen rather than hear about them years later, then stay here. Subscribe, because from now on, the universe isn't just out there, it is unfolding. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.